gate delay. So now let us see here. Okay. Let us see the an example where the gate delay and the as well as net delay is involved. Okay. So let us consider a small circuit here. So let us take a circuit. So let us take a circuit here. So it is a circuit. So where an OR gate is there. So let the inputs are A, B, C, D, and also here the output is Y here. Okay. Let this as Z1. So this as G2 and this as G3. So label names are G1, G2, and G3. So the inputs are A, B, C, D. So here there are two whites. Okay. So these are the two whites here. So these are the two whites. So let the whites be, let this wire be W1 and this wire be W2. So now let us think that there is a delay of there is some delay here. So delay for the whites is 2/1, and delay for the gates there is some delay for the gates. Now let us write the program here. Okay, small program with the delays. So the first one is module. So module gate delay is the module name what I have taken, or else you can take it as total delay. So module total delay, then followed by the outputs and inputs. So I am taking the output first. Output is Y, and the inputs are A, B, C, D. Okay. So after that, specify what are the inputs and what are outputs. So inputs are A, B, C, D. So specify the input A, B, C, D. So to specify the outputs, use output Y. So next, declare the whites here. Okay. So white. So take there is a delay of 2,1. Okay. So 2,1. The whites are W1 and W2. Okay. So 2,1 means, so whenever the wire is going from 0 to 1, the value in the wire is going from 0 to 1. So there is a 2 units of time delay. So whenever the value in the wire is coming from 1 to 0, that is 1 to 0 propagation. So the delay of 1 time unit. So now specify the gates here. So and let us take hash 3,4 G1 is the label name. So the output of first G1 is W1 and the inputs are A, comma B. Similarly, specify the second gate, and so let's take the inputs delay are 5,6. So G2 is the label name. So on the output is W2 and the inputs are C, comma D. So whenever you are writing the AND gates here, that is a great primitives. Make sure that first we are writing the outputs, then followed by the inputs. So next gate is OR gate. So the let the delay of this gate is some 8,7.
Sir.
Hello.
Sir, your screen is not visible. Your screen is not visible.
Is it visible now? Is it visible?
Sir. No, sir. No, sir. It's not visible.
I have shared my screen. It is showing that I am sharing.
Yeah, visible, sir.
Okay. Is it visible, Suresh?
Yeah, visible, sir.
Okay. So one.
Select the writing pad, sir.
Hello.
No, select the writing pad, sir. Writing pad is.
No need. So that I have done already. Now it is visible.
Okay, now visible, sir.
So here what I have done is, so I have taken the OR gate here, OR. Okay. So OR 8,7. Okay. So here the label name is G3. and the output is y, and the inputs are w1 comma w2. Okay, so next end module. So end module. So this is the program what we have written here. So after we have specified the delays here. Okay, so wire 2 comma 1, so as well as AND gate, the delay is 3 comma 4, the AND gate G2 with the delay of 5 comma 6, and OR gate is having the delay of 8 comma 7. Okay, so now let us see how the output will be. So take the time steps here. Okay, these are the time steps. So now for example, so if it is 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So these are the time delays. Okay, so at 0 instance of time, the value of a is 0, and the value, sorry, let the value of a as 0. So and the value of b, let it be 1 here. Okay, so at C, let the C be also 1 and D also 1. Okay, so initially these are the values. So next what happens here after 2 units of time? Okay, so after 2 units of time here, the values will be changed. Okay, so the values will be changed here. So now A becomes 1 here, and B becomes 0, and C will be remain the same, and D becomes 0 after 2 time units. Okay, so now we have to plot W1 and W2 now. Okay, so initially what happens? So after changing the value, so W1 should become 0. Okay, so W1 is nothing but A, B. Okay, so when you change at 2 time units, so what happens is that, or else what you do is, yeah. So these are AND gates. So let's see it also 1. Okay, so after B, what happens is that, so A is 1 and B is 0. So therefore the output will be 0. So output will be initially at 0. So now what you can see is C is equal to 1. Okay, C is equal to 1, and let D also is 1. Okay, C1 and D1, or else initially D is 0 and let D becomes 1 at 2 time units. Okay, so now what happens? Initially C is equal to 1, D is equal to 0. So but now what happened here is that, so C becomes 1 and D becomes 1. So therefore the output, G2, what happens? So it becomes 1 here. Okay, so but here, so the AND gate G2 is having a AND gate of 5 time units, since the output is going from 0 to 1. So it is the delay when the output is going to 0 from 0 to 1. So therefore the output will not change at 2 time units immediately. So the output changes at a 5 units time here. Okay, so that means at 5 time units the W2 becomes 1. Okay, so at 5 time units the W2 becomes 1, and the W1 will be remaining the same. So now after that what happens when we get the output Y here? When we get the output Y means, okay, so we have changed the value of 2 time units, but there is a delay again here. Okay, so wire delay is 2 comma 1. So initially when you give 0, initially what we have given? We have given 0, 1 and 0, 1, 0. So the output is 0, 0 and it is 0. So initially the output is 0. Okay, so now when we have changed the D is equal to 1, so this part of the output becomes 1 and the total output becomes 1 here. So the Y will not go to 1 immediately at 2 time units. So it takes all the delays here. Okay, so what it does is is that it takes the delay here. So W2 at what time it has become 1 here? The W2 has become 1 here at 5 time units. Okay, so W2 has become at 5 time units. So now for the OR gate, so whenever the output is going from 0 to 1, the OR gate is having a delay of 8 time units. So therefore 5 plus 8, that is after 13 units of time. Okay, after 13 units of time, the 13 units of time, so the output of 5 goes to 1. So like this, you can able to determine the combination of net delays and the gate delay. So directly you cannot take the output at instant of time when you are having the gate. Here what you are doing is that first we have to take care of the wire delays here. Okay, so after that we have to calculate the gate delays after wire delays and again the gate delay. So like this you should do the delay calculation. So when you are going for the writing of a program using the and net delays. The next type of delay what you are having is the delays with
Sir.
Hello.
Sir, explain it once again, sir. Quite little.
So I will take a smaller circuit. It will be very easy for you to understand. Yeah. So take a small circuit here. Okay, so here we have the AB inputs. So after that, so it is the circuit here. Okay, so this is the circuit. So AB are the inputs. So the AND gate is having, it is take as G1, label name as G2 here. So the AND gate is having a delay of 2, 1, or else you can take a delay of 2, 2. So OR gate is having a delay of 1, 2 for suppose. Okay, so for here there is a wire here. So the wire is having a delay of 1, 1. Okay, so as I told you, so 2, 2 means whenever the output logic of this AND gate is going from 0 to 1, so there is a delay of propagation delay of 2 time units. Okay, so whenever the output of the AND gate is coming from 1 to 0, so there is a delay of 2 time units. So similarly, here there is a wire here, so which connects the two components. Whenever the wire logic comes from 0 to 1, there is a delay of 1 time unit, and whenever the wire logic comes from 1 to 0, so there is a delay of 1 time unit. Similarly for this NOT gate, so whenever the output of this NOT gate goes from 0 to 1, there is a delay of 1 time unit. So whenever the output of NOT gate comes from 1 to 0, there is a delay of 2 time units. Now let us write a small program for this. So module circuit, output is Y and the inputs are A, B. Okay, so next declare the inputs and outputs separately. A, B are the inputs, so therefore input A, B, and the output is Y. So similarly declare the wire. So whenever you are declaring the wire, we have to declare the delay also. So wire, so we have specified the delay. Wire is having a delay of 1, 1. So let it be W1. Okay, so similarly when you are specifying the gate delay, specify the delay also. So and hash 2, 2. Okay, so G1, so output of the AND gate here is nothing but wire W1. So the inputs are A, B. So similarly take a NOT gate. So NOT gate hash 1, 2, the delays associated with this gate, and G2 is the label name, and output of this NOT gate is Y and the input is W1. So this is next end module. Okay, so this is the thing how you can write the program. So now when you are writing, seeing the result here, how you get the result means. So let me explain with the time slot. So 0, 2, 4, 6, 8, 10, 12. Okay, so give the inputs here. So A, B are the inputs. So initially A and B are 0, 0. So after some time the value of A becomes 1 and the value of B becomes 1 at 2 time units. Okay, so initially what happens here, when A is equal to 1, so when A 0, B 0, the output of this, okay, the output of this AND gate will be 0. Okay, So after that, since we are giving the input to this NOT gate, the output of the NOT gate, that is y, becomes 1. So initially the output will be, y output will be 1. Okay. So after 2 units of time, okay, what happens is that, so I have changed the output of A and B to 1. So therefore, the output of AB becomes, what happens? The output of AB becomes 1 and the output of NOT gate becomes 0. But it will not change immediately. So in the waveform, we cannot change the output to 0 immediately. Okay, so it will not be changed to 0 immediately. So what happens is that, why? Because so there is a delay here. So there is a delay associated with it. There is a gate delay as well as the wire delay as well as the gate delay. So for example here, previously the AND gate output is 0. So now it is going to 1. So that means the AND gate output is changing from 0 to 1. So as per the delay specifications, if the AND gate output is changing from 0 to 1, there is a delay of 2 time units. Okay. So there is a delay of 2 time units. Once again, in the previous case, what happened? The wire, okay, the wire has carried, in the previous case, the wire has carried a logic of 0. Okay, so now the wire is carrying a logic of 1. Okay, so therefore, whenever the wire has logic from 0 to 1, so it is having again a delay of 1 time unit, that is 2 plus 1. And now in the previous case, the value of y is 1. Now it is becoming 0. So whenever the output changes from 1 to 0, so there is a delay of 2 time units. So that means, so after 2 plus 1 plus 2, that is after 5 time units. So after 5 time units means, so 2 plus 5, that is 7. So after 7 units of time, the output y becomes 0. So even though we have changed the inputs at 2 time units, because of the delays associated with these AND gate and NOT gate and y, okay, so the output y changes to 0 at 7 units of time. The output will not change instantly, but the output will change at 7 units of time. So this is the thing we have to make sure whenever we are going for the delay. So we have to add all the net delay and the gate delays associated with the signal propagation. So next one is delays with tri-states, with the tri-state gate. Okay, so delays with the tri-state gates. So tri-state gate means, so which gives the output as 0, 1 and it gives the output as high impedance state. Okay, so the output will be a tri-state here. So normally there are 4 types of tri-state gates. First one is buff if 1, buff if 0, not if 1, not if 0. So these are the 4 tri-state gates. Okay, so buff if 1 means, buff means buffer. Okay, buffer means which gives the same output whatever the input will give. So here it is the buff if 1. Okay, so this meaning is it is a buffer. It acts as a buff if 1 means whenever the control input is 1, whenever the control input is 1, the output is same as that of the input. The out, or else you can take it as I and you can take it as y. So y is equal to I whenever the control input C is equal to 1. So it is the buff if 1. So it is the symbol of buff if 1. Okay, it is the symbol of buff if 1. So buff if 0 means, so here the conditional input is a not. Okay, so that is if the conditional input C is equal to 0, if the conditional input C is equal to 0, so then the output y is equal to, so the output y is equal to the input when the conditional input C is equal to 0. Okay, so it is the symbol for this particular buff if 0. Okay, so next, not if 1 and not if 0. Okay, not if 1 and not if 0. So take a NOT gate. So it is a NOT gate here. The input of this NOT gate is I. So the output of this NOT gate is Y. Okay. So I am given conditional input here. So it is C is the conditional input. So if the conditional input in this NOT gate, so is C is equal to 1, then the output Y will be the inverse of the input. So it is the symbol for not if 1. Okay. So next, not if 0 means, so you take a NOT gate and the conditional input has to be the negation. Okay. So therefore here, if the conditional input is equal to 0, whenever the conditional input is equal to 0, the output will be the reverse of your input. So it is the not if 0. So these are the 4 tri-state gates which you are having in the Verilog. Okay, so and these are the symbols of these tri-state gates, as well as, so these are the representation of the gate primitives. Okay, so now let us see the how you can give a delays for the tri-state gates. Okay, so for example, take the buff if 1 gate. So buff if 1. Okay, here we have to take the label name. Okay, so that is, for example, buff if 1 hash. Okay, 1 2 3. So G1, the output is Y, the input is I, and the conditional input is C. Okay, so this how you have to define. Okay, the first output in the buff if 1 declaration is output. The second input is the input what you are giving, and third input will be the conditional input. Okay, so here we have given the 3 values, 3 time units. Okay, the first one is the first one is nothing but the delay associated when the output is going from 0 to 1 transition. So whenever the output Y is going from 0 to 1, the delay associated with this 1 time unit. Okay. So next one is when the output delay, that is the delay of the output Y is coming from 1 to 0, that is from 1 to 0 transition, the delay associated with the gate is 2 time units. And the next one is the delay for the output to go to the high state whenever C changes from 1 to 0. Okay, so whenever C changes from 1 to 0, what happens? The output goes to the high impedance state. Okay, so whenever C goes, whenever the delay, sorry, whenever the conditional input changes from 1 to 0, the output goes to Z. The delay associated with the output going to Z is nothing but 3 time units. So this is how you can specify it. So for example, if you take a buff if 1, so buff if 0, so buff if 0 hash 2 comma 3 comma 4, so G1 Y comma I comma C. Okay, so what is this meaning here? So whenever the output of the buff if 0, it is going from 0 to 1, that is the output is going from 0 to 1, so then the delay associated with is 2 time units. So whenever the output of the buff if 0, it is going from 1 to 0, so the delay associated with is 3. So now when you are coming for the 4 here, whenever, so it is the delay associated with the output whenever the output conditional input goes from 0 to 1. So it is buff if 0. So whenever the conditional input becomes 1, the output becomes Z. Okay, so it is the delay of the output when the output is Z, that is when the conditional input goes from 0 to 1. So this is the declaration of buff if 1. Okay, so this is how you can declare the delays associated with the tri-state gates. Okay, so for example, there are some more delays how you can specify here. So for example, if you are taking the buff if 1 here, so buff if 1 hash, you can specify like this. So buff if 1 is to 2 is to 3 comma 2 is to 3 is to 4 comma 3 is to 4 is to 5 comma G3, so Y comma I comma C. So it is the one type of delays we can specify in the Verilog. So here what is the meaning is that the output, okay, so the output ranges from 0 to 1, okay, with a minimum value of 1 time unit. So that means if you are doing the programming, or if you are sending multiple data bits, that is if you are changing the inputs regularly, so if you are writing like this means, so as I told you previously, it is whenever the output changes from 0 to 1. Okay, so it is the output changes from 1 to 0. So it is the conditional input. So when the output is Z, that means the conditional input goes from 1 to 0 in case of buff-if1. Okay, it will be the same when you write like this, but so the initial one denotes that it is the minimum delay. So whenever you change the inputs rigorously, so the minimum delay associated with the buff-if1 when the output is changing from 0 to 1 is 1 time unit. Okay, and the typical delay, that is the average delay or the typical delay associated when you change the inputs regularly, that means the output Y goes to from 0 to 1 is 2 time units, and it is the maximum delay. So 3 is the maximum delay associated when the output changes from 0 to 1 when we change the inputs regularly. So these are the first one denotes the, so these three denotes the minimum delays. So this is the average or the typical delays, and this is the average or typical delays, and this is the maximum delays. Now for example, if you take a AND gate here, okay, so if you take an AND gate, so AND hash 1, so 1 is to 2 is to 3, comma 2 is to 3 is to 4, G1, Y, comma A, comma B. So what is the meaning of these? A, comma B are the inputs and Y is the output. Whenever the output changes from 0 to 1, so that is during the raise time of the output, the gate has a minimum delay of 1 time unit. So and it is having a typical delay of 2 time units and maximum delay of 3 time units. Okay, and it is having a maximum delay of 3 time units. Similarly, whenever the output is going, that is the fall time, whenever the output is coming from 1 to 0, the minimum delay is 2 time units, typical delay is 3 time units, and the maximum delay is 4 time units. So this is how you can specify the different delays that are associated with the AND gates. So far we have seen the so after this, so far we have seen how to write the AND gate level circuits, and also we have seen the different data types, and also we have seen the operators. So before going to the next level of writing the next model of writing the program, so let us see how you can write a test bench. Okay, so how you can write the test bench. For example, I want to simulate some circuit. Okay, so if I want to simulate a circuit, so this circuit, it is the circuit I want to simulate. So for this circuit, we will be giving the inputs and we will checking the outputs. Okay, so these inputs can be given in many ways. So normally what is the case is that you can give the inputs by forcing the values, or else the best thing is that you can write the test benches. So whatever the inputs we want to give, the test cases, we can write the total test cases in terms of a test bench program, and we can assign this test bench program to this circuit. Okay, so that means CUD, it is the circuit under design. For this circuit under design, we have to write the test bench. Okay, so it is the circuit which we want to test whether the circuit which we have written is working properly or not. So it is the circuit which we want to test. So over the circuit under test, we have the test bench here. Okay, we are giving the input values to this test bench, and there should be a connection from this test bench to the CUD. So after giving the inputs to this circuit under design, so our circuit under test, so the output of this will be again has to be given to the test bench, and at the test bench we are able to see the output. Okay. So this is that. Therefore, the test bench here is the top level module. Okay, the test bench here becomes the top level module. So whenever we are writing the test bench for a given program, so the normally the test bench becomes the top level module here. So this we have to remember. So whenever we simulate a program with the test bench becomes the top level module. So the circuit under design or circuit under test will be the sub module of that. So this we have to remember. Why? Because sometimes what happens is that even though we have written the circuit under test correctly, but we fail to write the test bench properly. So at this time you get the errors, and we may not able to solve that errors properly. Okay, so the test bench program is also a Verilog module. So let us see how you can write the test bench program. So for example, first module syntax of test bench. Okay, module name. Okay, module name. So this can be the any module name, but it should be a proper identifier. Here there's nothing, we have to give the list of port names. Okay, so no need to give the list of port name. And next we have to specify the registers. Okay, so I'm not exactly following the same syntax. So what is in the text book? So just I'm telling in the easy method how to write a text bench. Okay, so register. So here registers are nothing but, so whenever you use the inputs to the test bench, that inputs have to be specified to the circuit under test. So therefore, one by one we have to give it. So whatever the inputs you are giving, so these are stored in the registers. So after that, they will be given to the circuit under test. So therefore, whatever the inputs you have declared, so whatever the inputs you have declared in your main module, that should be declared as registers. Okay. Next, so after getting the output from the circuit under test, we have to connect this output to the test bench output. So therefore, we are taking it as while. Okay. So next, while declare the outputs. So these inputs and outputs should be the same names, so which we have given in the designing module. Okay, so after that we have to specify the test cases by using the initial or always block. Okay, initial or always block. So with the time units. Okay, so after that specify initial or always block, begin the initial or always block, specify the time units. So after that, end the initial or always block. So then followed by, we have to instantiate for which program you are writing the test bench. So now here what you should do is that, so it should be the design, that is the circuit under design model name should be there. Okay, so then followed by the label name, then followed by the list of port names as it is. So after that we can use the system task in order to print the output. So after that, end module. So it is the test bench structure. So let us see a small example here. So first I will take an AND gate here. So AND gate, AND 2, the output is C, the output is C and the inputs are A, B. So specify the output C, input A comma B. Okay, so after that, AND G1 C comma AB and end module. So this is the program what I have written. So now for this I have to write the test bench. For an AND gate, we have the inputs as A0, B0, A equal to 0, B equal to 1, A equal to 1, B equal to 0, A equal to 1 and B equal to 1. So now write the test bench program here. So first module module name. So what I am writing, under 2 TB. So that is the test bench of and gate. Okay. So after that, whatever the inputs we have specified in your main module, that should be declared as registers. Okay. So register reg is the declaration of registers. Reg a comma b, declare the output as whites, white C. So this you have to follow. As I told you, the inputs must be declared as registers in the test bench, and in the outputs they are declared as while. Okay. So now after this declaration, we have here you can call the main module here also, or we can call after the declaration of initial or always block. Okay. So initial. So let us see about the initial block. So initial begin. So here we have started the initial block. So initial begin means, so whatever the data we are writing under this initial begin, so these values will be assigned only once to the particular variables. So what I have done at 0 time units. Okay, at 0 time units, what I am doing is that, so I am specifying the value of a equal to 0 and b equal to 0. So that means at 0 time units, the value of a is equal to 0 and the value of b is equal to 0. As 2. So that means after 2 time units. So after 2 time units, the value of a is equal to 0 and the value of b equal to 1. So I am writing the test cases. What are the probable inputs we have to check? Okay, in order to verify the functionality of this circuit, so what should be the inputs we have to give? So all these test cases we have to write. Next, again after 2 units of time, a equal to 1 and b equal to 0. And again after 2 units of time, a equal to 1 and b equal to 1. So like this, we have to specify all the input test cases. After specifying all the input test cases, end. So we are ending the initial statement what we have begin. Okay. So the meaning of the initial is, so these assignments will be done only one time. So these assignments will be done only one time. So if you are using always means, that will be repeated. That we have to understand. Okay. So after that, next we have to call the program for which we have written the test bench. So I have written the test bench for which program? Under 2. Okay. I have written the for the module under 2, I have written the test bench. So therefore I have to call that module. So the module name for which I have written the test bench is under 2. Okay, under 2, followed by the label name. Any label name. So this label name is optional here also. So any label name, and the name the list of port names as it is. Okay. So how we have listed the list of port names in the main module, we have to list as it is here. Okay. So after listing the port names, next we have to specify, if you want to, we have to specify up to which time we want to simulate that we have to specify. Okay. So before that, so there are some system tasks. So if I am using a system task known as monitor here. So if I use this command, what happens is that I can get the waveforms. Okay, I can get the waveforms. Apart from this, the values will be plotted. If you are using the monitor or display commands, okay, what happens is that, so the output values will be plotted. Okay, so initial monitor. So $time. Okay, so $time means what happens here is that it will specify at which time we are getting what result. Okay, $time. Here A is equal to percentile B. Okay, A is equal to percentile B means, so whatever the values you want to plot, you have to specify that. So A is equal to percentile B means I want to plot the value of A. So the A is binary value, so it is percentile B. If it is hexadecimal means percentile H. If it is octal means percentile O. If it is decimal means percentile D. Okay. So since A value is binary, I want to plot that means it is A is equal to percentile B. So similarly B is equal to percentile B, comma output next what it is y is equal to percentile B. Okay, y is equal to percentile B. So these values will be plotted. Okay, so these values will be plotted. Whatever we are given in the double inverted comma, the same thing with the respected value it will be plotted. So now we have to specify at A is equal to what value we have to plot. I have to plot the input A. At B I have to plot the B value. At Y I have to plot the Y value. Okay. So A, B, comma Y. If you change here means, so instead of if you change Y, A, B means the values will be printed first output then the input. So here whatever we are specifying, so it is important. Here in the double inverted comma, so it is for our prescription. So whatever in the double inverted commas will be there. Here first we have specified A. So therefore A is equal to that particular value of A will be printed. So like this. So after that, next, so this initial statement, since we are using the initial statement here, this monitor command will be executed only once. So after this again initial, so next we have to give the simulation time. Okay, so ash 20 $20 finish, ash $20 finish end module. Okay, so ash $20 finish means, so up to 20 units of time is your simulation time. The simulation time is up to 20 units of time, and the dollar finish means automatically the simulation will be closed. So dollar stop and dollar finish are the two things. So which specifies the simulation to stop. So there is a little difference between this. So we will see in the coming cases what is the difference between dollar finish and dollar stop. Okay, so it is the test bench module. So now what happens when you come to the execution of this program means, so first module and TB, so then the cursor comes here, so register AB, so then it understands that the compiler, so the AB are the input values and C is the output value. So next it will come here initial, okay, begin. If there are only single statement, in these cases, in these two cases, after writing the initial, we have not taken begin and end. Why? Because so in the initial there is only one statement, so therefore no need to write the begin end. If you want to write the multiple statements between the initial block or always block, we have to use the begin and end statements. Okay, so initial, so that is the initial statement is begin. First at 0 time units. So at 0 time units, when the time is at 0 time units. So initially, if you are not specifying the simulation time units, it will take it in nanoseconds normally. Okay. So initially at 0 time units. So the value of A, what you are specifying, the value of A is equal to 0. The value of B is equal to 0. So after that, it comes here, the cursor comes here, okay, and to G1 comma CAB. It looks for the module, with the module name as _2. So then the cursor goes to the main module here, okay. So now it will see, okay. So what is the logic here? And G1 comma C comma AB, that means AB are the inputs and C is the output. So I have specified A is equal to 0 and B is equal to 0. So the AND operation of A and B is 0, 0 means AND operation will, C output will be 0. So here C you take, I have taken Y, okay, C, okay. So therefore it comes here. So it will plot now. What it will plot? So after time at 0 time units, A is 0, B is 0, C is equal to 0. Okay. So the simulation time is at 0 time units. Okay. But the simulation will be end at 20 time units. Again, it goes to the here. So plus 2. So 0 plus 2 and after 2 units of time again. So the input values A equal to 0 and B equal to 1 will be specified. If A equal to 0 and B equal to 1, the AND operation is C equal to 0. Now, again after 2 units. So again after 2 units means, So 2 plus 2, that is after at 4 units of time. So even though we have given 2 time units, here this hash 2 hash 0 specifies that. So after 2 time units, so initially at 0 time units, after that it is at after 2 time units means 0 plus 2 at 2 units of time. So whenever the cursor comes again here, the value of A1 and B will be given at 2 plus 2 at 4 units of time. At 4 units of time, the value of A is equal to 1 and B is equal to 0 will be specified, and C value becomes 0. And after 2 units of time means at 6 units of time. At the 6 units of time, A equal to 1 and B equal to 1. Okay, then C becomes 1. Then the output C is equal to 1. But the simulation time is at 20 nanoseconds. So that means up to 20 nanoseconds, the simulation output will be the same. So for example, this is the outputs what you plot. But when you come to the waveform here, okay. So when you come to the waveform, so 0, 2, 4, 6, 8, 10, and so on up to 20. So initially I have taken A is equal to 0 and B is equal to 0. So therefore the value of C is also 0 initially. Now after 2 units of time, A equal to 0. Okay, so A is 0, B becomes 1 after 2 units of time. So B becomes 1. Okay. So again after 4 units of time, that is at 4 units of time, A value becomes 1, A value becomes 1, and the B value becomes 0, and the B value becomes 0. And again after 6 units of time, so A becomes 1, so A will be 1 and B will be 1. Okay. So now initially at 0, 0, C will be 0, and A0, B1, C will be 0, and at 4 units of time, A1, B0, C will be 0, and at 6 units of time, A equal to 1 and B equal to 1. So therefore the value of C becomes 1. Okay, the value of C becomes 1. So but the simulation end time is 20 time units. So in the program what we have done means the simulation end time is 20 time units. So therefore up to 20 units of time, the previous values only will be existed. Okay, that is A becomes 1 and B becomes 1 up to 20 units of time, and also the C output becomes 1 up to the 20 units of time. So this is the waveforms how will be plotted for the given test bench. Okay, for example here, uh, so we will write one more program for the small OR gate. By using that, we will explain the always block. Okay. So directly I am writing. So R2 is the module name of the OR gate. Okay. So module OR gate is R2. Okay. C comma A comma B. So after that, so the inputs are A comma B and the output is C. So after that, specify R2 G1 C comma AB. So next end module. So now write the test bench for this. Okay. So when you are writing the test bench for this module R2 test bench, module R2 test bench, declare the inputs as registers. So register A comma B, declare the outputs as whites. So white C. So next here, so we have to declare the initial block and always block. So now I take declare the always block here instead of initial block. So always begin hash 2 A equal to 0, B equal to 0, hash 2 A equal to 1 and B equal to 0, hash 2 A equal to 0 and B equal to 1, hash 2 A equal to 1 and B equal to 1. Okay. So after specifying this, so next end the always block. So after that, if you want to print the values means you can use the monitor command which I have shown you. So if you don't want the values to be plotted, if you want directly the waveforms to be shown. So directly you can go for initial. Okay, so after some 16 units of time, so dollar finish. So after that end module. So it is the test bench what we have written. So now let us see how the waveforms will look like. Okay, so 0, 2, 4, 6, 8, 10. These are the time units which I am plotting here up to 16. Okay, so initially A is equal to if you coming here at 0 at 2 time units. So directly I have assigned the value at 2 time units. Okay, so from 0 to 2, the value of A is unknown and the value of B is also unknown from 0 to 2 time units. Why? Because initially I have assigned the value of A equal to 0 and B equal to 0 to 2 time units. Okay, with the delay of 2 time units. So the C also undefined 0 to at 0 to 2. Okay, so after 2 units of time, after 2 time units, what happens? A becomes 0. So up to this point it is unknown. So now it becomes 0. So again 2 plus 2. As 2 means after 2 units of time. So previously the specifications were at 2 time units. After 2 time units means 4 time units. The value of A becomes 1 and the value of B will remain as 0. So again after 2 units of time, that means at 6 time units the value of A becomes 0 and the value of B becomes 1. And again after 2 units of time the value of A becomes 1 and the value of B becomes 1. Okay, so now what happens here? 0. So OR gate. So A is 0, B is 0. So up to 4 units of time, the C output is 0. So after that, when A equal to 1 and B is equal to 0 at 4 time units, the value of output C becomes 1. So and again after 6 time units. So what happens? A equal to 0 and B equal to 1. So it remains as 1. And again at 8 time units, A equal to 1 and B equal to 1, the output value will become 1. But now you see here, the simulation time will be ending at 16 time units. And moreover, we have used the always block. So initial block means the values will be assigned only once. But always block means these values will be repeated. Okay. So after 8 time units, A equal to 1, B equal to 1. Again repeat it. Okay. So again plus 2 means after 10 units of time, the value of A becomes 0. The value of B becomes 0. Okay. So initially when you are using the initial statement, the last values will be present up to the simulation end time. But when you are using the always block here, what happens is that when you are using the always block, so again the values will be repeated. So after 8 units of time, sorry, 2, 4, 6, 8, after 10 units of time, the value of A becomes 0, B equal to 0. Okay. Next, at again plus 2, that is after 12 units of time, again the value of A becomes 1 and B is 0. Again 14. So after 14 units of time, the value of A is equal to 0 and B equal to 1. And again after 16 units of time, the value of A becomes 1 and B becomes 1. So here, so like this, it will stop. At 16 time units, it will stop your simulation. So now based on this, so here at time 10 units, it becomes 0. From 12 again, it becomes 1 up to 16. So like this, you get the simulation waveform when you are simulating with the always block. So it is the major difference between the initial block and the always block when you are using in the test bench. Okay. So if you are following any model, okay, you can write the program in the any model, but the test bench is same if you are writing the program in behavioral model or data flow model or the gate level model. Okay, so for this AND gate OR gate, if you write the programming in the behavioral or data flow, the test bench is similar. So there is no change in the test bench programming. So the test bench program is not confined to one model. Here what we will do is that in the test bench we are not defining any logic. So in the test bench we are providing the inputs that are required for the simulation. So whatever the simulation inputs are required, or whatever the test cases we want to check, that inputs are given to the module. But here we are not defining any logic in the test bench. So whatever the logic is present, that entire logic will be only defined in the main module, that is in the circuit under design or circuit under test. Okay, so this is how to write the test benches. So for anything, so for any program, you can write the test benches like this. For example, let me take a simple AOI gate here. So under invert gate. So it is AB under invert gate, CD. So then followed by the OR gate, then followed by the invert gate. Okay. So it is the output device. So let us see how you can define the test cases for this. Okay. So G1, G2, G3, G4. So coming to the program, how you can write? So module AOI gate. So what is the output here? Y. Inputs are A, comma B, comma C, comma D. So you remember that the port names, the list of port names in the module definition can be inputs followed by the outputs and outputs followed by the inputs. So after that, specify the inputs. So input A, comma B, comma C, comma D. After specify that, output Y. Okay. So after specifying the output Y, so next specify wires here. So here there are three wires. So one is connecting between the G1 to G3, G2 to G3, and G3 to G4. So specify the wires here. So W1, W2, and W3. Okay. So wire W1, comma W2, comma W3. So after specifying the wires here, so next write the gate primitive declaration one by one. So the first one is AND gate, whose label name is G1. So the output is W1. The inputs are A, comma B. Similarly, AND G2 is the label name. The output is W2, and the inputs are C, comma D. Okay. So next is OR gate. The label name is G3. So the inputs output is W3, and the inputs are W1, comma W2. Okay. So the next one is NOT gate, whose label name is G4. The output is Y, and the input is W3, and end module. So this is the program for this. So coming to the test bench, how to write the test bench here. So the first thing is module. So test module name. So AOI test bench. Okay. So after that, specify the inputs as registers. So registers A, comma B, comma C, comma D, and declare the output as Y. So wire Y. So next, here you can instantiate your main module. Okay. So after writing the initial block, you can instantiate, or after writing the initial block, you can instantiate. Okay. So my main module name is AOI gate, followed by the label name and list of port names. So Y, comma A, comma B, comma C, comma D. So after instantiating your module name, the next thing is we have to give the test cases. So initial begin. Okay, initial begin means the values will be given only once. Okay. So here there are 4-bit input, so there will be 16 test cases. So normally, in order to verify the output perfectly, we have to give all the test cases. So at 0 time units, so specify A equal to 0, B equal to 0, C equal to 0, D equal to 0. Okay. So next, at 2 time units, A equal to 0, B equal to 0, C equal to 0, D equal to 1. Okay. So you can give the value like this, or else you can give the 1-B0 also. So this, if you are giving like A equal to 0 and D equal to 0 or D equal to 1 means, so by default the compiler will take that these are the binary numbers. If you want to specify the inputs in hexadecimal numbers or anything, so you can specify like this. For example, 2b dash 1 1. If you are specifying to any input, for example, there is a vector input which is a 2-bit vector input in the program. We have to specify the test cases like this. 2 dash b111 means, so a is a 2-bit vector, so whose value I have specified as 1 1. Okay. Similarly, I can give the if you want to give it as 1 dash 0, that is the decimal number 0 with the input as 0. Like this, we can specify it. So next, again after 2 time units, so a equal to 0, b equal to 0, c equal to 1, and d equal to 0. So again after 2 units of time, so a equal to 0, b equal to 0, c equal to 1, d equal to 1. So like this, I can specify all the 16 test patterns. So after specifying all the 16 test patterns, so I can end the initial module or always module. So these time units, whatever the time units I am specifying, so these time units is your wish. Okay. So depending upon your thinking and depending upon your program skills, so you can assign this time units. Okay. So after that, next, if you want to see the output waves to be values to be plotted in terms like this, so you can go for initial monitor, so which will display the values. So $time, so in order to display the time here. Okay. Since for example, one more thing here. Okay. So for here, if you are giving 2.1 means, and if you are using the $time means, so only 2 will be printed. So if you want the time to be plotted in the decimal points, here we have to take the real time. Okay. So hash 2.1 I have taken. If I am using the time means, it will not consider this decimal point. In order to consider the decimal point means, we have to use $real time. Okay. So time. So a is equal to percentile b is equal to percentile b, c is equal to percentile b, d is equal to percentile b, y is equal to percentile b. So a comma b comma c comma d comma y. So after that, give the simulation time ending. So initial after 50 time units, $finish or $stop. So after that, end module. So this is how you can write a program for the AOI gate. Okay. So tomorrow what you can do is that, so I will meanwhile I will write some of the programs and I will show you in the model sim. So if with that you easily can understand so how the simulations will take place. Okay. So this is for the day. So I hand over to Suresh.
Hello, sir.
Suresh.
Oh, okay, sir. Yeah, you have any doubts, ma? Otherwise, now we close this session. Okay, in this week we have assessment. Okay, in this week we have assessment. Yeah, thank you, sir. Now we close this session.